what I want to convey to you in 29 minutes, because we don't have time to go through all of it. How many people have taken something like something on numerical in algebra before? So counting flops for various matrix factorizations, matrix vector operations. Can you raise your hand? Oh, so not as many as I thought. How many people are familiar with the basic concept of a flop? OK, so I think almost everybody. So let me go through this part really quickly. Just going to remind you what a flop is. This is not necessarily central, like I said, to convex analysis, convex optimization. But the reason I put it here is because the next algorithm unit we're going to see is second-order methods. And second-order methods involve solving linear systems for updates rather than just performing an update that looks like move in the direction of the gradient. And it's important to understand that that's more expensive and why that's more expensive, and when that can be maybe way more expensive versus a little bit more expensive. So that's why we're going to talk about this part now. Now that the first order methods are mostly, in a sense, behind us. So what's a flop? A flop stands for a floating point operation. So literally, it counts one addition, subtraction, multiplication, or division of two floating point numbers as performed by your computer. That's the definition of a flop. It serves as a basic unit of computation when you think about the complexity of a certain kind of sequence of operations. It's not perfect. Okay, it's not an operation as performed by your computer. For example, it doesn't count a comparison, right? If I just compare one floating point number to another, that costs 0 flops according to this definition. But it's still, you could still think of that as costing like a basic unit of computation if you defined it in a more general sense. So sticking with the definition of flops, how much do basic vector-vector operations cost? Let's just go through this very quickly. If we have two vectors in Rn, adding two vectors costs n flops. So just add, for example, each one component of one vector with the other, right? So there's a total of n additions I make. Scalar multiplication, so multiplying a vector c by, a scalar c by a vector a costs n flops again. Now it's just n scalar multiplications. An inner product costs 2n flops. Right, it's actually 2 times n minus 1 flops. 2 times n minus 1 flops, but on the order of 2n flops, right? Because we do n multiplications and then essentially n additions added all together. But these are all linear in n. That's the point. Okay, all these vector-vector operations just cost something linear in n. Here's an example of why flops are imperfect. What happens if I asked you to think about how much it costs computationally to set every element of a to 0, or every element of a to 1? That costs 0 flops. Okay, so just that, for example, sequence of n operations costs 0 flops according to our definition. Okay, so again, imperfect measure, but it's a fundamental unit of computation that's well defined, which is why we use it. So let's just go through again a few basic operations and think about how much they cost in terms of flops before we come to kind of the meat of this mini lecture on numerical linear algebra, which is solving linear systems. How much does it cost to multiply a matrix by a vector? Okay, let's say we have an m by n matrix A and an n vector B. It always helps me, by the way, to just draw pictures. So I won't draw pictures for every one of these things, but it always helps me just to draw pictures for this kind of stuff. So that's A and that's B. How much is it going to cost to multiply B by A? Compute the product AB. Well, I have to take for example, n multiplications when I take the inner product of any one row with B. And in fact, we already saw what the inner product costs, which was for two vectors. It costs 2n, so I actually have to perform 2n flops for each one of these inner products. And I have to perform m such inner products, right, one for each row. So the total cost is 2 times n times n. So again, on the order of m times n, which just makes sense from drawing yourself a picture and staring at it. How about if A is sparse? So I told you that A was sparse. It only contained s non-zero entries instead of m times n non-zero entries. Okay, if you stored those cleverly, then that would only cost 2 times s flops. So why is that the right order? It's because I only ever need to multiply, for example, an element of s times an element of B, an element of A times an element of B if that corresponding element of A was non-zero, right? And there's only S of them, so I'm going to just be performing S flops, okay? Because I have essentially S multiplications and S additions there. So much, much cheaper than M times N if S is small compared to Mn. How about if A is banded? So a k-banded matrix means one that has, we typically think of them as square, but k-banded just means that in any row, there are only k non-zero entries. So, and these are all zeros. That's what a k-banded matrix looks like. Okay, in any row, there are only k non-zeros. So, for the same reason as an m by n matrix, when I multiply such a matrix times b costs 2mn flops, a k-banded matrix only costs 2nk flops. It's because I actually only need to ever operate on kind of this banded portion, right? So I can actually think about this. You can always think about a k-banded matrix as actually, for example, an n by k matrix, right? It's just been kind of indexed a bit differently. Another special case, so this is the general case. These are all special cases for which it's faster. If A is a low rank matrix, and I actually have the explicit representation for it, so I write it as a sum of ui vi transpose from I going from 1 to r, where r is maybe reasonably small. That means that A is a low rank matrix. This is a factorization. I'm writing it as a matrix U times V transpose, but here I'm just writing it out in terms of the columns of U and V. That only costs 2 times R times n plus n flops. Okay, so it's a lot cheaper than M times n if R is small. And I'll leave you to think about why this is true. It just comes right from, well, you can think about it in multiple ways, but just think about it in terms of the inner products and stuff you need to perform as per the previous slide. Okay, and just to emphasize again that our definition of a flop is imperfect. If A is a permutation matrix, multiplication is free, costs 0 flops. So you're in luck, according to this definition, because all you're doing is you're just rearranging elements of B, right? There's no multiplication, division, addition, or subtraction going on. So we really do think of that as costing, say, order n, but in terms of some kind of more general notion of computational unit, but in terms of flops, it's just 0. Okay, so matrix vector products under our belt. Matrix products. Think of a matrix product, right? I have m times n times n times, say, p or something. That's A and that's B. It's going to cost 2 times m times n times p flops. So just think of that as a more general version of this, where I do it for each column of B. I perform this multiplication for each column of this matrix B. It's exactly what the matrix product is. So it multiplies this cost, 2mn, by the number of columns, which is p. So it's 2mn times p. If A was sparse, for the same reasons as above, it's going to just cost 2 times s times p flops. So again, a lot cheaper. Even cheaper than that if B is also sparse. So matrix multiplication, again, can be a lot cheaper if the matrices are sparse. Just wanted to note, matrix vector product. I'm sure this is something that you guys know from basic programming, but of course, this can be done one way or another in terms of kind of association, how you group things. And it can either be pretty expensive on the order of a matrix product or a matrix vector product if you do it properly, right? What are the two different ways to do it? If I think of A times B times C, I can think about that programmatically. Let's say if I was going to implement that in MATLAB or something, as first take the, let's say, the product between the matrices A and B. So that's a matrix product. And then take the product with the vector C. And that's actually fairly expensive because we have to compute a matrix product. So that's in the order of MNP. Or we could perform BC first, which is a matrix vector product, and then A times that vector, which is again a matrix vector product. And that's just going to be in the order of n times p or m times n, whatever's bigger. Okay, so a lot cheaper. So fairly basic notions. We went over all these things quite quickly. But let me know now if there's anything unclear, because That's kind of our basis for what's to come. No? Okay. So solving linear systems, that's what we're going to spend the next 20 minutes talking about. And by the way, this is, people devote their entire careers to this. This is a research field. It's, I'd say there was more research in numerical linear algebra probably 20 years ago, but there's still ongoing research for sure today. And we're just going to see kind of a glimpse of how all this is performed. It's a lower level of optimization, right? It's, again, a field in which implementation is extremely important, but we tend not to think about this because, we treat that as a black box, and we're opening up the optimization black box. But, for example, another course might treat this topic in detail over the course of a semester, solving linear systems. So how do we compute the solution to ax equals b? That's what we're going to talk about. In general, this costs about n cubed flops. Okay, A is an n by n linear system, n by n matrix here. We'll see more on this in just a few slides. How about special cases? If A is diagonal, it only costs n flops, right? Because we just do n divisions. It's quite easy. If all A was a diagonal matrix with diagonal entries A1 through AN. If A is lower triangular, which means that Aij is equal to 0 for all j bigger than I, so it means that A looks like this. Okay, that's a lower triangular matrix A. Then by using something called forward substitution, we can solve it in only n squared flops. Okay, what do? We just solve the first linear equation we have, which tells us that A11 times x1 is equal to b1, because all the other entries of the first row of A are 0. And that's very simple. It's just one division. Then we carry that forward, and we solve the second linear equation in our system, which tells us that A21 times x1 plus A22 times x2 is equal to b2, right? Because again, in the second row, all the other entries are 0 beyond that. And we know what x1 is from the first step. So we just form this residual, b2 minus a21 x1, and divide by a22. That gives us x2, etc. And we carry forward like that. And you can convince yourself that this actually costs on the order of n squared flops, right? For example, this alone is going to be costing us n flops, the last step. And there's n of them, n steps here, so it's going to cost on the order of n squared flops. For an upper triangular matrix, so this is lower triangular. Upper triangular just means that it's the kind of the opposite of this. So everything is 0 below the, so this is lower triangular. This is upper triangular. For the same, same reasons, it costs n squared flops to solve a linear system in A. Now we do backward substitution. So we start with the last linear system and go back up. I'll just mention a few other special cases. If A is S sparse, so it means it has S non-zero entries, often costs a lot less than n cubed flops. But exact worst case flop counts are not known if you just tell me that there are S non-zero entries in A. Okay, so worst case is still going to be n cubed according to kind of our most sophisticated worst case analyses. It's because it's a kind of too generic problem. So you have to kind of give me a little more information about the sparsity structure when it comes to solving linear systems if you're asking me theoretically for a fast algorithm for solving sparse linear systems. Now in practice it costs a lot less than n cubed flops, on the order of n if S is much less than n squared. But worst case bounds don't really reveal that. We're talking about direct methods for linear systems. Some special cases of sparse matrices, so all these ones below are special cases, and these have enough structure that we can actually say that worst case we have pretty fast linear system solvers. If A is banded with bandwidth k, okay, so it's this guy, then it costs n times k squared flops to solve a linear system in A. So if k is constant, if I have a n by n matrix where n is big like thousands and k is small like 10, then this is a linear time algorithm effectively, right? I only have to use order n flops in order to solve a linear system. So much, much cheaper than solving a full dense linear system in A. For orthogonal matrices, It's also a special case. It's not sparse, but it's specially structured. And the inverse of A is just its transpose for orthogonal matrices, which is so computing x equals A inverse B only is the same thing as computing a matrix vector product, which is n squared flops, another special case. And for permutation matrix, again, according to our definition, it's free, costs 0 flops, because it's a special orthogonal matrix where the orthogonal matrix itself, so the transpose itself, is another permutation matrix. Okay, so I would think of this in my mind as costing order n computational units, order n operations, but cost 0 flops for the definition. Okay, so this is an overview of different types of linear systems, how much they cost. Just important to note that dense linear systems are way more expensive than sparse and structured ones. Okay, for example, banded linear systems are much, much cheaper to solve. So how do we actually solve linear systems in practice, or how does MATLAB do it? When you call A \B, for example, we're talking for the most part today about direct linear system solvers, and those are based on what are called matrix factorizations or matrix decompositions. So the idea behind that is to factorize A as a product of matrices, so A1 times A2 all the way through AK, where K is usually 2 or 3, so this factorization is usually pretty small. And then instead of computing A inverse times B, so solving that linear system outright, we actually solve a sequence of linear systems. We first solve A1 times x equals B, and then we take the solution to that and we solve A2 times x equals whatever that was, etc. So we perform a sequence of linear system solves, right? Because of course, if I think about all these as invertible, then the inverse of A is just the product of the inverses of AK through A1. And the reason this is preferred is because usually these A's are very special. These A1s through AKs are very special. So they're usually orthogonal, triangular, diagonal matrices, or permutation matrices. So we usually try to achieve a factorization that makes A1 through AK kind of have a special form, and that puts us in these cases here we talked about. Banded orthogonal permutation, sparse, something like that. Okay, that means that each of these linear system solves, for example, A1 inverse B, is a lot cheaper than the original linear system A inverse B. Okay? It's also very useful to factorize A because it's useful for settings in which we want to solve many linear systems in the same matrix A. So suppose I gave you A times x equals B, and you solved it, and I said, OK, now I want you to solve A times x equals B prime. So that actually happens fairly common. It's fairly common in practice that you'll encounter linear systems one after another all in the same matrix A. And once you compute the factorization of A itself, right, so once I actually compute a product A1 through AK that gives me A, I can use that factorization for any linear systems I encounter downstream. So it can be much more efficient to do so than just to solve this outright, right, for each right-hand side, B or B prime, B double prime, etc. OK. That's the high-level motivation for matrix factorizations. I also want to mention, actually, that if you have a factorization of A, and I do something like make a rank 1 update to A, then it's often very efficient to get a new factorization for A from the old factorization. So simple changes that I apply to A often we often have ways of updating the factorization to get a new factorization for A given the old one. So here are the two kind of canonical matrix factorizations that are out there, Choleski and QR. And I think I'm actually not going to go through pretty much any of the details of Choleski or QR. I just want to give you the punchline. Choleski is a factorization that exists for any symmetric positive definite matrix. And I can write any symmetric positive definite matrix as the product of a lower triangular matrix times its transpose, LL transpose. It costs n cubed flops to compute the Choleski factorization, so for an arbitrary matrix A. So just computing it once costs as much as solving a linear system in A. But then, right, the advantage is that I can actually solve linear systems using the Choleski factorization in only n squared flops. So if I asked you to solve 1,000 linear systems in A, right, the cost would either be 1,000 n cubed, if you solved each of them individually. Or it's n cubed to get the Choleski factorization plus 1000 n squared, right, if I use the Choleski factorization to solve each of those linear systems. Okay, so once I have the Choleski factorization, it's n squared computation flops to get the solution, but it took me n cubed to get it in the first place. I'm just going to have to skip this and go right to the second guy, QR. So the counterpart, kind of the close friend or close cousin of the Choleski decomposition, is the QR decomposition. And here we think about factorizing matrices that are actually rectangular rather than square. So any rectangular matrix has a QR decomposition, where Q is an orthogonal matrix and R is actually an upper triangular matrix. So it's again very special, orthogonal times upper triangular. And I can compute it again on the order of n cubed flops if A happened to be square. And solving linear systems costs on the order of n squared flops with the QR decomposition. Do I have that here? Why did I not put that on the slide? Maybe I put it on the next slide. So it's roughly the same cost as Choleski to compute, and roughly the same cost to solve linear systems once you have the QR decomposition. What are the main differences between Choleski and QR? So I just wanted to point this out. Not some people are always aware of. The punchline is that Choleski is cheaper. It's actually like a factor of 2 cheaper in general to compute a Choleski decomposition versus a QR decomposition. But the QR decomposition is more stable. So the details are on the slide. You can go through them if you're interested. But even though matrix factorizations in principle give us the exact solution, if you had a perfect computing environment, round off errors in your computer and other kind of numerical inaccuracy issues mean that you never get the exact solution to a linear system. And the QR decomposition is more stable in the sense that it tends to be more accurate. Okay, so it's a trade-off between stability, or sometimes we call that sensitivity to condition numbers, versus raw speed. So Choleski is a little faster, QR is a little bit more stable. The default in MATLAB, if you do A/B, is to use a QR decomposition. I think it uses, you can go through just look up some like forums or help files from MATLAB. It actually has kind of like a flow chart, tells you when it uses what matrix factorization. It uses Choleski in some cases, certainly if the matrix is square and positive definite. But it tries to check that the matrix is kind of well enough conditioned before it applies the Choleski composition, because it's not as accurate as the QR decomposition. Okay, so either can be used for minimizing least squares losses, for solving problems of this form. I didn't go through the details, but they're on the slides. And just think of these two things as the punchline. Okay, the differences between Choleski and QR. Advanced topics I just put here. We're not going to have obviously any time to go through that. Just maybe make a note that sparse matrix factorizations are a topic of current research. And like I said, worst case bounds for sparse matrix factorizations aren't really known, or they're not very sharp, that is. And some people, like for example, Tim Davis. Tim Davis is a researcher at the University of Florida. He has a book called Direct Methods for Sparse Linear Systems. And he has this like wonderful C package called, or C library called Sweet Sparse, that gives you the analogy of a sparse of a Choleski decomposition for a sparse matrix and a QR decomposition for a sparse matrix. So you can think of these as all the sparse counterparts to all your favorite matrix factorizations. This is actually good enough. Tim Davis is an academic. This software is good enough that this is what MATLAB itself uses when you call A/B and A is sparse. So if you call A/B in MATLAB and A is sparse, it uses the sparse QR decomposition from this library. So it's really like top code. I just want to make you aware of this. There's a whole other world to solving linear systems outside of matrix factorizations. And there's a high-level distinction between them, which is that the ones I mentioned just now are called direct methods. A whole other world is to approach linear systems with indirect methods. And the difference between the two is that direct methods aren't by nature iterative. So you don't iterate arbitrarily long to get a closer and closer solution. It just provides you with the exact solution, assuming you have a perfect computing environment. So if you had a perfect computer, there was no errors with kind of round off and overflow, whatever else cause numerical inaccuracies on the computer. Direct methods would give you the exact solution. An indirect method wouldn't. It's like gradient descent, for example, is an indirect method. You iterate it more and more to get a more and more accurate solution. So indirect methods, the two kind of most common ones for solving linear systems, or let's say the two most basic ones, are Jacobi iterations and Gauss-Seidel iterations. You basically iterate through solving a linear system in each variable. Okay, so I try to solve the linear system in question in the variable x1, and then I use the residual and try to solve the linear system in x2. The difference between them is whether or not I carry the updates forward after every pass through the variables, or after I take one pass through the variables, whether I update the residual all at once. That's the difference between Jacobi and Gauss-Seidel. And we're going to see that this actually has a close analogy in optimization, which is coordinate descent. You could perform gradient descent on this criterion in order to solve the linear system ax equals b. Okay, that is a perfectly viable method for solving that linear system, right? Because if I take the gradient here, it looks like ax minus b equals 0. So the solution to that linear, the minimizer to this problem is going to be the solution to ax equals b. But it's for a very, very large problem where a is sparse. Instead of using matrix factorization, I may think about applying gradient descent. Now that's not really usually done in practice, but I'm just telling you that it's a possibility. And here are the gradient descent updates, right? That's the gradient, and that's what I would do. I would update in the direction of the negative gradient. Conjugate gradient is much more commonly used in practice over gradient descent as an indirect method for solving big linear systems. And just to make you aware, like I said, of this other world, conjugate gradient descent, or conjugate gradient method, you can think of actually as a variant of gradient descent on that criterion, but where the conjugate directions are designed to make the set of updates you see more diverse. So the problem with gradient descent when I apply it to this criterion is that the gradient directions I see actually aren't very diverse as I run the algorithm. So the updates aren't very efficient, and how fast that converges depends very strongly on the condition number of A. So I can converge very slowly if A wasn't well conditioned. Right? Whereas direct methods, we saw their runtimes were in terms of flops. They have nothing to do with how poorly conditioned the matrix A is in terms of their speed. They always pretty much cost the same, regardless of the conditioning of A. Indirect methods depend on the conditioning of A, just like we saw that gradient descent depends on the condition number of the Hessian. Okay, it's the same reason here. Same with conjugate gradient, it's just the dependence is a little bit better. It's not quite as bad. Still, it can depend kind of heavily on the condition number of A, and so people use things called preconditioning, which try to think about it as transforming the problem ax equals b to one that has better conditioning, and then you run conjugate gradient. This is often done when A is sparse without structure, because in that case, like I told you, the worst case bounds for direct methods are not really known, and sometimes people might not want to use direct methods for sparse linear systems because they're not super well understood. You can see the gradient descent steps, and it's actually going to be the same as the conjugate gradient descent steps. They only involve multiplication by A. So when A is sparse, they're very cheap, and so people typically use these methods for solving large sparse systems. So that was a real whirlwind tour of numerical linear algebra. People often get confused about the distinction between direct methods and indirect methods when you use one versus the other. So let me just close by repeating something that I actually read Tim Davis write. He wrote about this. He's an advocate of direct methods for linear systems. He says that if you ever have a linear system that can fit in memory, if you fit A in memory, then you probably want to use a direct method, okay? Because that's the regime in which direct methods excel. If you have A that's big enough that doesn't fit in memory, then indirect methods are your friend. So that's just kind of a rough rule of thumb. So obviously for most of the homework problems and whatnot, we'll be on the scale of matrices that fit in memory. So when you solve linear systems, you use the MATLAB / operator. It goes with direct methods. But sometimes in real applications, you get these really big linear systems, and maybe it's really expensive just to store A in memory, or it's a big enough problem that at least memory is a concern. That's when indirect methods start becoming really appealing. All right. If you have any questions about that, it was rather quick. Come to my office hours. Otherwise, I will see you guys on Thursday.